Hello, this is your instructor, Richard Collins. Welcome to Heat and Energy Transfer, Unit 4 of ATM101, Weather and Climate of Alaska. This unit explores two topics, energy and heat in the atmosphere, and Arctic haze. The questions we'll be looking at is, how does energy enter and leave the atmosphere? How is energy transmitted and absorbed in the atmosphere? How do energy balances and imbalances drive the weather and climate? And does the meteorology of the Arctic contribute to Arctic haze? This lecture supplements our textbook, Weather, A Concise Introduction by Gregory Hakim and Jerome Patou, and draws on the work of Glenn Shaw, a former professor at the University of Alaska who studied Arctic haze. Before we get into all the details, let's take a look at the big picture. Consider how much energy enters and leaves the atmosphere over the course of a year over the whole globe as a function of latitude. We see that the energy from sunlight is mostly absorbed in the tropics and decreases toward the poles. The energy lost by the Earth back to space varies less dramatically with latitude. At latitudes equatorward of 38 degrees north and 38 degrees south, the annual gain is greater than the loss, and we have a surplus. At latitudes poleward of 38 degrees north and 38 degrees south, the annual loss is greater than the gain, and we have a deficit. Thus, we would expect that each year the lower latitudes would get hotter year by year, and the higher latitudes would get colder year by year. This is an unstable situation, with apologies to fans of Vin Diesel, Richard Riddick, necromongers, and crematoria. That does not happen. Instead, the excess of energy at low latitudes is carried poleward by our weather systems. This is the fundamental reason that we have weather. Energy is transferred by the processes of conduction, convection, and radiation. Heat conduction is the transfer of energy in a body due to temperature differences in the body. The speed of the conduction increases with the temperature difference. The physical process by which conduction occurs is transfer of kinetic energy by vibrating and moving particles. As particles bump into each other, they transfer energy. So the energy is transferred like a bucket of water in a bucket chain, where the people in the chain do not move, but the bucket moves along the chain. Importantly, in the atmosphere, air is a very poor conductor of heat. Still air conducts heat 100 times less effectively than granite. We know this from our homes when we use cavities of still, dry air as part of our insulation. As a result, conduction is mainly important in transferring energy between the atmosphere and the ground, close to the Earth's surface. Convection is the transfer of energy through fluid, either liquid or gas, motions. A fluid next to a hot surface is heated and usually expands. The expanded blob of fluid is now less dense than the fluid around it, and so it is buoyant, and it rises and carries its energy with it. So we have heat convection, transfer of energy by fluid motion. We see convection every day when we boil water in a saucepan. Rolling convection occurs in the pan, just as it does in the atmosphere, where the warm, less dense parcel of fluid rises, then cools, becomes denser, and falls back down to the heat source. In the great outdoors, the ground is first heated by the sun. The ground then heats the atmosphere above it by conduction. The heated air becomes buoyant and rises. We can see this convection in action on a summer afternoon in the Tanana Valley. In the afternoon, the hills north of town are heated sufficiently to cause rising columns of warm air called thermals. As the air rises, it cools, we will discuss this more later, and the water in the air condenses, forming cumulus clouds. So as you watch cumulus clouds form in the afternoon, you are watching convection. Birds around the world soar on the thermals, using them as a free elevator. On our Throat-Yedja campus, you can watch ravens soar and play in the thermals created by the power plant. Radiation is the transfer of energy by electromagnetic waves. The theory of energy transfer by radiation is one of the great achievements of the 19th and 20th century physics. All objects at temperatures above 0 Kelvin, minus 273 Celsius or minus 459 Fahrenheit, emit radiation. Waves are defined by their wavelength and frequency, where the frequency and wavelength are related through the speed of light. The wavelength of an electromagnetic wave can vary from 100 meters, or a frequency of 3 megahertz for AM radio waves, to 500 nanometers, or 6 by 10 to the 14 hertz, or 6 terahertz for visible light, to 1 nanometer, 3 by 10 to the 17 hertz, or 300 petahertz for X-rays. As objects heat up, they become both brighter and change color. Cooler objects appear dull red, hotter objects appear bright blue-white. So the wavelength of the light emitted by an object increases as it gets hotter. This is conceptually consistent. Hotter objects have more energy, and waves with shorter wavelengths are more energetic. The fact that hotter objects get brighter is quantified by the Stefan-Boltzmann law, attributed to Joseph Stefan and Ludwig Boltzmann. The power per unit area, or watts per meter squared, emitted by an object is proportional to the fourth power of its temperature in Kelvin. The fact that the color changes as the object heats up is quantified by Wien's law, attributed to Wilhelm Wien. The wavelength of the brightest color is inversely proportional to the temperature in Kelvin. These laws highlight the fact that Kelvin is a fundamental measurement scale. Kelvin, unlike the arbitrary scales of degrees Celsius and degrees Fahrenheit, has no negative value. As we cool to 0 Kelvin, the radiation emitted decreases to 0 watts per meter squared, and the wavelength increases until there is no wave, as the wavelength approaches infinity. Finally, the Planck curve developed by Max Planck describes the distribution of the radiation with wavelength or frequency for an object at a given temperature. The theory used by Planck ushered in the age of modern physics and quantum mechanics. We can now address the radiative properties of the Earth and Sun. The Sun is at an average surface temperature of 6,000 Kelvin and emits light at a wavelength of about 550 nanometers, or half a micron. The Sun emits 70 megawatts per meter squared of energy. The Earth, at 300 Kelvin, 20 times lower temperature than the Sun, emits radiation at a wavelength of 10 microns, 20 times longer than the Sun. The Earth emits about 460 watts per meter squared of energy. Looking at the Sun at 500 nanometers, we see the photosphere, the visible outer shell of the Sun from where the light is radiated. Looking at the Earth at 6.5 microns, we see swirling features indicating emissions from cloud and water vapor in the troposphere, obscuring the surface of the Earth. Atoms and molecules absorb and emit equally well at a given wavelength. If the particle absorbs well at 500 nanometers, then it should emit well at 500 nanometers. When molecules absorb energy and store it as kinetic energy, they warm up. When they emit infrared radiation, they lose kinetic energy and cool down. Around trees, we often see depressions in the snow that arise from a mix of absorption and emission. Visible light falls on the trees and warms them up. The trees then radiate that energy as infrared radiation. While snow reflects visible light and appears white, it absorbs infrared radiation strongly. Thus the snow warms up and melts around the trees. On the right, we see the absorption spectra for several gases. These indicate the wavelengths for these species: nitrous oxide N2O, methane CH4, molecular oxygen O2 and ozone O3, water vapor H2O, and carbon dioxide CO2 absorb radiation. For example, nitrous oxide and methane absorb radiation in narrow bands at wavelengths between 1 micron and 10 microns. Ozone absorbs broadly at wavelengths below 0.3 microns, or 300 nanometers, and in a narrow band at 10 microns. Water vapor absorbs broadly at wavelengths longer than 1 micron, with a broad band at 6 microns. When we add the absorption spectra for the 5 gases, we see that there are some distinct regions. First, in the 400 to 700 nanometer region, there is little absorption. Visible light travels through the atmosphere, and sunlight can reach the ground from the top of the atmosphere. The atmosphere appears transparent, and this region of the spectrum is called a window. Second, in the 8 to 11 micron region, we again see that the atmosphere appears transparent, and we again have a window. These window regions are very important in remote sensing as they allow satellites to see to the ground. We see increasing absorption at wavelengths greater than 1 micron, and third, at wavelengths longer than 10 microns, there is strong absorption by water vapor and carbon dioxide. Atoms and molecules have distinct orbitals where electrons can reside. Each orbital has a given energy. If the energy of the wave matches the change in energy between orbitals, then the atom molecule will absorb the energy, and the electron will move from the lower energy orbital to the upper energy orbital. The parcel of wave energy is called a photon. If the photon energy does not match the change in energy, the atom will not absorb the energy and the electron will not change orbital. Once in the upper orbital, the electron can fall back to the lower orbital and re-emit the photon. In some molecules, such as ozone, the molecule absorbs the photon, and then that increase in energy allows the molecule to split apart. Ozone absorbs radiation and then photodissociates into atomic oxygen and molecular oxygen. Thus, the layer of ozone in the stratosphere forms a shield against ultraviolet light as the ozone absorbs ultraviolet light and forms atomic oxygen and molecular oxygen. Molecules have energy levels associated with vibration and rotation of the molecule. The energy levels associated with vibrations and rotations are much less than those associated with electronic transitions. Again, the photon's energy must match the energy of the change in the vibrational and rotational states. Electronic transitions are associated with ultraviolet and visible radiation. Vibrational and rotational transitions are of lower energy than electronic transitions and are associated with infrared radiation. Light that is not absorbed is reflected. The percentage of the light that is reflected is called the albedo. The albedo can vary with the wavelength of the visible radiation. Usually, visible wavelengths, 400 to 700 nanometers, are assumed when we talk about albedo. For example, fresh snow has an albedo of 80 to 90%, meaning it reflects 80 to 90% of the incident sunlight, while it absorbs 10 to 20%. Ice with an albedo of 30 to 60% absorbs 40 to 70% of the incident sunlight. This is the opposite of water with an albedo of 10%. Water absorbs 90% of the incident radiation. Thus, as the Arctic Ocean becomes more snow and ice free, it transitions from a high albedo to a low albedo, to a reflector of energy to an absorber of energy. As it absorbs more energy, it warms further, melting the snow and ice, reducing the albedo and allowing further warming. This is the example of a positive feedback. In this scenario, what would happen if clouds form over the open water? Would the positive feedback be disrupted? Scattering is where particles, such as aerosols, molecules, and atoms, interact with incident light and change the direction of the light. Scattering depends on the relationship between the wavelength and the size of the particle. The daytime blue sky and the red sunset sky both arise from scattering. The daytime blue sky arises due to scattering of sunlight by the molecules and atoms that are several hundred times smaller than the wavelength of light. These particles scatter blue light more strongly than red light, following a lambda to the -4 behavior. Thus, blue light at 475 nanometers is scattered 4 times more strongly than red light at 675 nanometers. The blue light is scattered out of the beam of sunlight and then ricochets around the sky, creating the blue dome of the daylight sky. At sunset, the light travels a long distance in the atmosphere. The blue light scatters out of the direct beam, leaving the red light to travel toward the observer and create the red sky.